So, hi everybody. What I'm going to do now is I'm going to discuss quantum harmonic oscillators as a preamble to non-classical light. I know a lot of you have seen this in your undergraduate course and maybe a bit tired of it, but this is very important because the electromagnetic field, if it's quantized, is going to behave like a collection of quantum harmonic oscillators. And these concepts of quantum harmonic oscillators are useful in very many areas. For instance, in quantum field theory, quantum optics, etc., etc., etc. So we're going definitely to have a look, even if it's quickly, to pave the ground for what we're going to discuss next. So we are going to then have a look at the quantum harmonic oscillator today. And our motivation is really how we are going to describe light in a quantum mechanical way, especially a light field. So this is a widespread system studied in quantum physics, and I'm sure a lot of you are familiar with it. So I'm going to be brief. This is the Hamiltonian associated with quantum harmonic oscillator, where here we have the P operator, the X operator. We have a quadratic potential, which can be very useful in many instances. And we also know that the eigenstates of this system are a set of equally spaced energy levels. Equally spaced is very important, and they are labeled like this, n. And n is an integer number. And we also know that the eigenenergies, they are given by this expression, where n is going to go from 0 to infinity. And you can view this as if the energy were quantized into equal packets. So each equally spaced level that you reach, you have to give a quantum of energy. And this is a very useful picture for us. And we also have special operators to go up or down the ladder. Namely, we can define an annihilation operator, and we can also define a creation operator. And the annihilation operator and creation operator, they are actually having opposite relations with regard to each other. A dagger is the taken with regard to this guy, and A applied to n, any state n is going to bring it down up to the state n minus 1. So that's why it's annihilating operator, because it's annihilating something. And if you wish, it's annihilating a quantum of energy and is bringing this guy down. Now, if you want to create or give energy to the system to make it go one up, you apply a dagger to n. And this is going to give you then that it moves from n to n plus 1. And you can also show that they don't commute. They satisfy this commutator relation. So a commutator with a dagger is equal to the identity. This is very useful because depending on the problem you're solving, you may need to reorder things. And also we can define a number operator. So if you have an operator that we apply to a state n, and this operator is given by a dagger an, you just get the eigenvalue equation. So you get the integer number n. And this is viewed as giving the number of excitations that you have in that particular state. So in a state n, you would have n excitations. And what is very useful for us is that we can write the Hamiltonian in this kind of ladder operation picture as well. So you can write it in terms of h of a dagger a plus 1/2 multiplied by h bar omega. And if you remember, En, which were the energies, were given by an expression in which this guy, this operator a dagger a, was replaced by number n. So this is pretty much working in this way. And just to illustrate the picture associated with ladder operators, let's consider, for instance, that you have a harmonic oscillator. So you're going to have energy levels. Here is your first energy level. They are separated by h bar omega. And this means that when you make the particle, or a fictitious particle, if you wish, go up and down, you are creating or destroying something. So let's say if you give energy to make the system go to n minus n plus 1 from n, you are creating a fictitious particle in n plus 1. Or you can destroy a fictitious particle in n plus 1 and make it go to n. So you are creating a fictitious particle in n. And this is a concept that is used a lot in quantum field theory and quantum optics. So you can think about it as state 0 has no particles, state 1 has a single particle, 2 has 2, etc., etc., etc. And when we look again at the number operator, and we can write it in the ladder operator picture, I want to call your attention to the fact that we rewrote X and P in terms of A and A dagger. This is something that we can do. And you should note that this specific formulation is very useful for quantum field theory, quantum optics, and other formulations may obscure useful features as well. It depends on how you want to describe your system. Because, for instance, you could say, yeah, but I know how I do this in position representation. Yes, you do. What would you do in position representation? You would write your Hamiltonian. You would try to sort out everything in terms of position space wave functions. You would get some Hermite polynomials. And yeah, that would do the job. But is this easy? Is this what you want? Would you be able to see what you want to see? Because here the picture is very clear. You're going to be working in what we call Fock state space, because you have these guys here. In fact, they're called Fock states. You create one particle, or you get rid of one particle by applying the ladder operators. And if you want to probe what is the number of excitations in a state, you just apply this operator exactly. Very well. So we are now in a position to talk about non-classical light. And our key objective here is to obtain a quantum description of light starting from the classical Maxwell's equations. And such equations, they're going to be written in a form that we will be able to identify simple harmonic oscillators, and we're going to replace them by quantum harmonic oscillators. So we're going to have a look. I warn you that this is going to be a bit hand-waving because quantum optics is a vast research field. And our key motivation here is just to give you an introduction so that you know how this whole thing works. But this is very important. So let's start then from Maxwell's equation of vacuum. I'm not going to discuss these. You are supposed to know them from your electromagnetic theory course. So you have curl E minus dV dt, div E 0, div B 0, and curl B is proportional to dE dt, whereby this is the magnetic field and this is an electric field. So these actually, they give you wave equations for the electromagnetic waves. if you combine them using properties of the curl in, for instance, these, you are going to be able to show that the equations can be combined, and you can find a wave equation, which is actually given this way, and it's giving you how a wave, an electromagnetic wave, is going to propagate in the vacuum. And here 1 over c squared, where c is the speed of light, is this mu naught E naught. So these are constants associated with the vacuum, the electric constants, etc. And we can solve that equation using separation variables. So we can suppose that this ERT, here we didn't put the R on top, but bear in mind that this is the vector position. We didn't put the vec symbol, but it is what it is. And we have then T is a function of time. So we write ERT as UR times TT. And we have some separation constants, which are these ones. And we solve the whole thing. And we get 2 equations, one where you can associate with space, and the other which you can associate with time. So for space, you get this expression, which is only in terms of this UR. This is the Helmholtz equation. And for the time, you get something that is a harmonic oscillator. So we know that the solutions are going to be of this form, x plus minus I omega t. And the general solution then is going to be something like that. So this is the sum of independent oscillators, if you want. You have spatial functions, you have oscillators with frequencies omega j, and you're going to have also some weighted sum. So you have all these coefficients. This is like the most general form we could have for this electric field. And what you do to quantize is you replace classical harmonic oscillators with a quantum harmonic oscillators. And the energy eigenstates of each oscillator, they are going to represent a state of n photons in the nth mode. Sorry, I forgot here. In whatever mode that you have. If you want to know details, and if you want to really look at the derivations, check this book. It's really good. Modeling of Optical Coherence in Quantum Optics, chapter 10. And we can also state, because we are considering and we are writing these as a collection of quantum harmonic oscillators, that the Hamiltonian associated with each mode, with each mode, is given by this expression. And if you have many modes, you're going to be summing over them. So your total Hamiltonian is going to be sum over J, where J is a Hamiltonian associated with each of the modes. Then we can also write the electric field operator like this. Also a bit of work, not the end of the world, but is not the objective of this course to derive this expression here. But just bear in mind that it is going to be given by this expression in terms of AJ and A dagger J. And note as well that sometimes this myriad of modes, this wide range of modes, the fact that you are summing over modes, this can be quite convoluted and quite complicated for you. So it may be of interest to suppress some modes or enhance other modes, and this can be done by using what we call a cavity. So I'm not going to discuss this in detail, but when you have 2 mirrors, you can create resonances and you can destroy certain modes, enhance certain modes, or there's even something that is called cavity QED, cavity quantum electrodynamics, which is a huge area of physics in which you, by changing boundary conditions of systems, you can affect excitations, you can affect decay, you can affect many, many things. So a cavity is a great way of playing around with the boundary conditions of your system, and by doing that, affecting how the field and how the system behaves. And this can be made then to interact using a single mode, so that it simplifies your problem a lot. So we would have then that Hamiltonian would be given by this expression in terms of the number operator for a single mode, and your field would be given by this expression in terms of A plus A dagger, but again for a single mode. So thank you for watching. And next, we're going to see a very useful example, which is also fundamental in many areas of physics as an approximation, which is a two-level atom. And we really need to know how we're going to treat it. And this is the topic of the next lecture. Thank you for watching.